Lesson 28, we're going to try and finish up the notes in this next video here. It says, use the Maclaurin series of y equals cosine of x to determine the Maclaurin series of sine squared x. Okay, so again, what we're doing really overall now is we're avoiding using this obnoxious set of formulas here. We can continue to use them, but it's completely unnecessary if we can avoid them. So that's what we're going to do here, is we're going to try and avoid them. Now, what I'm going to do first is I'm going to say I want to use this series, so I'm going to go ahead and write that series down. I know that the cosine of x is equal to the even powers with factorials. Okay, so that means that this is going to be equal to a 1 minus x squared over 2 factorial plus x to the 4th over 4 factorial minus x to the 6th over 6 factorial. I think we get the picture. I'm going to stop writing them out now. The next thing I'm going to do is I'm going to say, well, wait a second. It wants me to use this to find out what the series is for this. So I'm going to write that down, sine squared x. How do I use this series to find this one? Well, we could try and change this using the Pythagorean identities, but then we're going to have sine squared is equal to, what was it, 1 minus cosine squared? And I don't want to square this thing. I mean, you saw in the last video how obnoxious multiplying two of these things out. That's not what I want to do. Okay, there's got to be something else I can do. Well, if you recall this particular identity, and I believe this identity is considered the half angle identities again, don't I have a way now to deal with, again, this being equal to 1/2 distributing the division, cosine of 2x divided by 2? And then if I just say, well, wait a second, if I look at cosine of 2x, that means that I'm going to take all of the x's in here and replace them with 2x. So I'm going to say the cosine of 2x is really equal to 1 minus 2x quantity squared divided by 2 factorial plus 2x to the 4th divided by 4 factorial minus 2x to the power of 6 divided by 6 factorial plus dot 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 and so on and so forth. So, what do I really have here then? Okay, what do I really have here then? Well, I have this stuff here subtracting all that stuff divided by 2. Okay, so I'm going to write this out very carefully. I have the 1/2 minus that entire thing, which I'm going to write out again, 1 minus, now I'm going to actually multiply these pieces out, so it's minus 4x squared divided by 2 factorial, plus, this is going to be 2, 4, 8, 16 x to the power of 4 divided by 4 factorial, minus, this is going to be 2, 4, 8, 16, 32, 64 times x to the 6th divided by 6 factorial plus dot dot and so on and so forth. This thing here divided by 2. Okay? So now what I'm going to do, very carefully, I'm going to distribute the negative, and I'm going to distribute this division of 2. So this is going to be equal to a 1/2 minus 1 divided by 2. Negative changes that to a positive, and it's going to be 4x squared divided by 2 times 2 factorial. I'm going to put parentheses on the 2 factorial because that's separate. The negatives are going to distribute and make this thing a negative, and I'm going to have 16x to the 4th divided by 2 times a 4 factorial. Okay, the next term, I'm going to distribute the negative and change this to a positive 64x to the 6th divided by 2 times the 6 factorial. Technically, I could keep this going at this point, could I not? I could technically say the next one's going to be a minus sign, and it's 4, 16, 64. If I multiply this thing by 4, that's going to give me my next term, so it's going to be x to the 8th. X to the 8th. 64 times 4, I'm not doing it in my head because I'm too lazy for that. 64 times 4 is 256. And this thing would be divided by 2 and 8 factorial. Okay, the last thing I would probably want to do is notice that these two things actually combine. This gives me that I'm going to be left with, and I'm going to simplify things down too. 4 cancels out with 2 and gives me 2x squared divided by 2 factorial. Minus These are going to cancel out and be left with 8 x to the 4th divided by 4 factorial. These are going to cancel out and be left with plus 64 divided by 2 is going to be 32 x to the 6th divided by 6 factorial. Minus, let's go ahead and do this next one. 256 divided by 2 is going to be 128 x to the 8th divided by 8 factorial. Okay. Now, very carefully, I'm going to change one more thing about this. One more thing. Just because it'll look nicer. That's 2 over 2 factorial x to the 2nd. Minus 2 to the power of 3 over 4 factorial x to the power of 4. Plus, isn't that 2 to the power of 5? 2 to the power of 5 divided by 6 factorial x to the 6th minus. Well, first power, third power, fifth power. I'm guessing this would be 2 to the power of 7th, and if you check it, it is 8 factorial x to the 8th plus dot dot dot. And now I can figure out the rest of the pattern and all the rest of the terms if I needed to. Now, the last question would be, where is this thing convergent? Where is this thing convergent? Well, let's go back through. This had an interval of convergence of negative infinity to infinity. I changed the interior of the function by 2x. Did I change what I can plug in here? No. The interval of convergence for this one will be negative infinity to infinity. Therefore, when I plug it into here, the interval of convergence for this whole thing will not change. So this thing down here, the interval of convergence, is equal to negative infinity to infinity. Okay, and that completes that whole problem. Lastly, use the power series to approximate this. Okay, and I'm sorry, there should be an extra piece here. The power series we're going to be using, okay, the power series we're going to be using here is, well, I'd go e to the x. Why would I use e to the x? Well, because e to the x, if I replace x with a negative x squared, that's what I'm seeing here. Okay, so what I can say is that e to the x, now I've got to remember that power series. That power series is actually 1 plus x squared divided by 2 factorial plus x to the power of 3 divided by 3 factorial plus dot dot dot. Again, that's what e to the x is. So it would be e to the negative x squared. Well, that means I'm replacing all of my x's in here with x squareds. Again, I'm replacing all my x's in here with a negative x squared. Again, the x in here is replaced with this. So the x in here is replaced with this. So this one's going to actually give me a 1 minus x squared, replacing the x with a negative x squared, plus a negative x squared, and then squared. A negative x squared squared is going to be a positive x to the 4th divided by 2 factorial. Next, I'm going to plug into here, and that's going to give me a negative again, because negative x squared cubed is going to give me a negative number. X squared cubed is going to give me x to the 6th. This is divided by 3 factorial, and so on and so forth. So let me just get the next term just so you see it. Okay, I'm going to have 4 factorial on the bottom, 2, 4, 6, I'm guessing 8, and then the next one's going to be a minus sign, dot, dot, dot. So if this is e to the x, e to the negative x squared is this, okay? What is it that I want to approximate? I want to approximate this thing right here, okay? What is this thing? Well, I want to integrate this thing then. So let me do that. The integral of e to the negative x squared from 0 to 1 is going to be equal to integrating all of these individual pieces. So it's going to be equal to x minus x cubed divided by 3 plus x to the 5th divided by 5 times 2 factorial minus x to the 7 divided by 7 times 3 factorial plus, and I'm going to go ahead and do this last one, x to the 9th divided by 9 times 4 factorial minus dot dot dot. If I plug in 0, this is the best part, all of these are zeros, right? 0 minus a 0 over 3 plus a 0 over, okay, so those are all zeros. So this is really going to be equal to 1 minus 1/3 plus 1 over 5 times 2 factorial minus 1 over 7 times 3 factorial plus 1 over 9 times 4 factorial. Now, the question that we'd have to back this up, okay, is I'd also want, and I'm going to go ahead and do it for this particular problem, approximate within 0.001. No, let's do just 0.01. Okay, let's approximate within this. How can we guarantee that the second decimal place is accurate? Well, notice this particular series is alternating. We have a remainder formula for alternating. Again, the overall remainder will always be less than or equal to the nth plus 1 term of the sequence. So what I'm going to do is I'm going to look through these ones and find the first one that's in here, okay, that gives me a value that's going to be larger than 1 over 100. 1 over 100. Okay, a value that, sorry, smaller than 1 over 100. Well, this is 1 minus 1/3 plus 1/10. This is good, but not good enough. Minus, this is going to be 3 times, 6, so it's 1 over 42. Not good enough. Okay, again, I can't add these 3 terms up and leave this one out, because I can't guarantee that this one here has a good accuracy for us. Looking at this last one, plus, this is 9 times 4 factorial. That's actually 1 over 216. That number is smaller than 1/100th. That number is smaller than 1/100th. So, my remainder will be less than or equal to 1 over 216, which implies that I have that this is less than 1 over 100, which means that this will be accurate within this range. Again, this summation of these terms will be accurate, okay, for this integral in that range that we're looking for. That number right here is approximately equal to, if we go ahead and do it out, is 1 over 216. Oh, sorry, not 1 over 216. This is going to be approximately 0.74. Okay, approximately 0.74. Which means that I can say, 0.74, that 0.7 and the 4 are both not going to change as I continue further. Okay, this next one will only change the third decimal place, which is perfect for us. That actually completes lesson 28. In the next set of videos, we will be talking about polar coordinates.